So hi and welcome to the CodeMavens meetings, the meetup group. And if you're watching the YouTube video, then to the CodeMavens YouTube channel. My name is Gabor Szabo. I am a self-employed. I help companies introduce Rust and Python, help them with training, help them with testing. And I also organize events, both in-person meetings in Tel Aviv and in Python for Python and Rust, and also these online events in English in order to share knowledge between people all around the world. And I think it's a very good way to learn about all kinds of things that we can't learn ourselves. This time we have Frans who agreed to give this presentation, and you're going to introduce yourself, or he's going to introduce himself in a bit. I'm really happy that you agreed to give this presentation, and I thank everyone who joined us in this meeting. Feel free to ask questions. After the recording, we can stay around. So if there are things that you don't want to talk about during the recording and in the YouTube video, that's fine. We can stay around after the meeting and have a little chat as well. That's the advantage of actually being in the meeting. And also you can ask questions. And if you're watching the video, then please click the like button and follow the channel so you get notified, and also join the CodeMavens meetup group so you will be able to see when we have new meetings. Frans, welcome to this meeting. Please introduce yourself, and it's yours. Share your screen if you like, whatever.
Yeah, thanks, Gabor, and thanks for the opportunity. As I just mentioned to you, unfortunately, I haven't got a formal presentation, but I will talk through the sort of process that went into what I'm doing. So first of all, my name is Frans Slabber. That's the full spectrum of names, and I'm a programmer living in South Africa. I've been a programmer since I can't remember. Since '94, mainly, I work for myself as well, so I do various contracts, developing mainly in the technical sort of programming space, solving modeling problems, etc., stuff like that. So my main expertise has always been C++. Recently, I'd moved into Golang a bit, and then I sort of, out of interest, started in Rust. So Rust is almost, I haven't, how can I say, used it commercially, but it's an interest, and it's a fascinating way for me to, I've got a strong interest in mathematics, especially how it relates to numerical computing, for use in machine learning and stuff like that. Very technical term. Okay, so first order of business. What I did is I'm going to share a screen because I think that's the easiest way to go about this. That's okay, Gabor, obviously.
Yeah, sure. Go ahead.
Okay, so I'm not too familiar.
Should be a big green button.
Yeah, I've got it. Share screen. Oh, yeah. Oh, not seeing it. Select window. So I'm going to select not that one. I don't know what that's doing. Open still. Allow Visual Studio. So I've got a very big screen. So please tell me if the resolution is okay.
Well, way too small, the letters. So if you could enlarge the fonts, that would be nice.
Yeah, I can just zoom in. I think that works as well. Just a moment. No, there is a... Yes, somebody wants to say something?
No, I'm just going to turn it off. It beeps when someone joins.
Oh, right. Just a moment. I've done this before. Sorry, guys.
No, is it Windows or
There we go. No, it's Linux.
Linux? So for me, it's Control Shift Plus usually.
Yeah, there we go. That's slightly better. Okay.
A little bit more. A little bit more.
Yeah.
More. One more.
Sure.
Yeah.
Wow.
Yeah. Okay. Thanks. That's now. No, at least I can see. I don't know if anyone else still needs larger. Please let us know. For me, it's fine.
Okay. Good stuff. So basically, let's go. Let's start at the beginning. So the first thing I started playing with is complex numbers. And the idea is to write a what in C would be a template class. To write the equivalent in Rust, and to actually have limiting it by means of traits. Okay, so sorry, let me just take a step back here. The whole idea that I started out with as well is that I wanted to write something. One of the main ideas is that it's completely safe code. So I don't call into any under the covers, call into any unsafe libraries, any C or C++ libraries. Of course, that comes with a performance penalty because you gain quite a lot by, for example, if to do your matrix arithmetic or matrix manipulation, to do that with pointer arithmetic is generally much faster. But I stayed away from it on purpose. So this is all safe Rust code, number one. And also, I then obviously the closest I could come in terms of performance is by using iterators extensively. So, okay, having said that, I started out with the basic ideas of a generic complex number class, and there are libraries out there that do it, and probably do it much better. So I've got no claim that I'm doing wonderful stuff, and as you can see, there's still quite a bit outstanding. But okay, sorry, let me just go to the top. So what I started up is just a basic struct, real, and imaginary with a type, a generic type T. And because I wanted to make this compliant with num traits, float and integer actually specifically, I had to define all the traits. Now, some of them I haven't completed yet because I didn't use them. So if we go down here, you will see there's some to-dos in there. There we go. Which is probably needs to be fleshed out at some point. So again, just reminding you that this is purely a fun project for me. I'm not beholden to anyone to have a finished polished product. Of course, I would like to move to that point, but hey, it's all dependent on when I have time or not. So that's my last excuse I'm going to make. Promise this evening. Okay, so complex numbers, not a big thing. There are things out there, pretty much. And I mean, I'm not going to dwell on this too much. This is, you can imagine, this is very basic kind of coding. Right. So, of course, that the aim of that was to start moving into matrices. So then I start. Okay, sorry. I just want to get to the matrix declaration. Apologies for all this scrolling around. Oh, boom. So what I decided on in terms of looking towards the future to store all the data in a flat vector, generic vector, and to make it row dominant. So what that means is that if you look at a matrix and you look at the first row, that would be the first. So say you've got n rows, n columns. So the first n entries in the vector is the first row, and then the second n entries that follow onto that is the second row. So I don't know if that creates a easy visualization, but that's for those that don't haven't heard about row dominance. Anyway, so and that was sort of then it started getting interesting. So the normal things like adding a matrix, subtracting a matrix, extensive use of or just iterator and all the goodies that it has with it. So that was pretty so interesting, but pretty straightforward. And then I added stuff like get the diagonal as a vector, etc., that kind of thing, and getting a skew diagonal. Also, I find that I wanted to, if you have a matrix of floats, you want to round them off to some decimal place, which is very nice. For later manipulation, I found I needed upper triangular matrices. So if any of these things, these are just different forms of matrices. So upper triangular is all the elements above the diagonal is non-zero, and the one below are zero, kind of thing. And as that is, and lower triangle is triangular is the opposite. And we have the famous identity matrix. So if this is, so I'm assuming some level of linear algebra background here. Uh, yeah, assumption. Then, checking if it is an identity, that kind of thing. Okay, so that's pretty much sort of what you would think it would have as a standard library. Then now, my and there's transpose. Of course, now this raises very interesting when you write this, because you have to keep in mind that you have a flat vector storing the stuff. So if you have to do a transpose, you have to carefully work with what they call strides. In other words, it is normally the offset that you would get to an element in a specific row and column in a flat vector, considering a flat vector. We will talk more about strides when we get to tensors. Okay, so this was sort of submatrix, and you can see there's some tests here. In a way, I wrote a macro for declaring a matrix like that, which is pretty straightforward. And then to get the submatrix, sticking to having this inclusive ranges that you can specify from this row to that row and from this column to this column inclusive, and it will give you the submatrix out of this chunk of bigger matrix. Anyway, so that's sort of what's going on here. Of course, this whole process also to keep in mind is that this is me. As you work with iterators more and more, it becomes clearer and probably less clunky working with it. Okay. So also doing stuff like inserting a row, inserting a column, etc., etc. Then, of course, there becomes augmentation, is where you're adding a sub matrix on top, as the description is up top here, the top left corner of a larger matrix. So when I start writing matrix, how can I say, routines, this becomes important. Determinant of a 2 by 2, and then converting a real to a complex matrix. Okay, so now we start seeing why I started with complex, because I wanted to work. My first aim in doing with this, or the first sort of goal that I had, was working with complex matrices. And there was a very specific reason that I wanted to do it, which I'll show later, or just now. put it that way. So now with matrices, you have very famous things like LU decompositions with Gauss elimination. So now it became really interesting. And I mean, I really actually love this stuff, sadly. I do other things in life as well. Just a side note, humorous side note. Anyway, so that was sort of this. I think this was my first big achievement. Was it LU decomposition with a partial pivot? Fascinating stuff. So, what I really liked about this is I did applied math degree long ago, but I you completely forget things because if you don't work with it, or not completely forget, but it's so far removed. And what was very nice is that I had to go and sort of read up on how these things work, especially uh, from a numerical computing point of view, because that is different to a sort of straightforward academic theoretical application of matrices, because computing isn't exact. So you always have rounding errors and you always have to work to a certain precision. Anyway, that was linear solving. Have I got to complex yet? Sorry about that. I just want to go up. Inverse, inverse of a real square matrix. No, we're still on real. Okay, so at some point, sorry, it must be completely boring. Sort of looking at what I did. Quite amazed that I wrote it all. Okay, so ultimately the point was to calculate eigenvalues of a matrix. So, and here I established then complex matrix specializations that where your a generic item is a complex matrix of T, which satisfies num traits. So there was just some things here, and then I think the ultimate is where I do. Oh, there's a random complex matrix, by the way, kind of things. Is where I actually. Oh, and a complex conjugate. So this is all to do with complex matrices, and this was also beautiful to do, complex matrix QR decomposition using householder transforms. This was fantastic. So by the way, all of this has been, how can I say, ratified against MATLAB because I wanted to make sure that I'm not putting nonsense out there. This is QR decomposition with householder transforms. So this is all used when you're trying to find the eigenvalues of a matrix. I just want to go right down where I actually do the, that's the householder transform, skew decomposition.
Yeah, I have a question, Frans. Did you
Yes.
do you so besides writing the crate, did you make any use of it?
No. So that's
for yourself or?
yeah. So I'm hoping to use it at some point. But at the moment, this was purely, as I said in the beginning, for myself as an entertainment, as something fascinating for me to do. And I enjoy mathematics and I enjoy solving complex software problems. And a lot of this coding um, is I maybe I'm just old and slow, but I find it very involved, and quite a lot of pencil sketches had to be done to figure out how to do this.
I mean, I
I have
see you use generics and all kind of interesting parts of Rust.
yes.
How did you did you implement anything similar in C++ earlier?
No,
How do you
I've
compare? How do you compare what the feeling of writing Rust? That's what I'm trying to ask.
much more difficult. And look, I mean, obviously, I've written C++ for what 20 years, so and template programming, template libraries is pretty because you have all these restrictions, these things,
Right.
making. And if you so for example, if you are doing an eigenvalue decomposition, you are using previous qr or lu decompositions that you've written to actually facilitate that finding that eigenvalue. And you have to be so how can I say careful to have the right traits from the bottom up. Otherwise, you can't. When you get to the top one, you don't satisfy the traits required to do it, kind of thing. If that makes some sort of sense, I just find it very. I mean, I appreciate what it's trying to do here in terms of forcing you to be very strict what you can do, and obviously that is the selling point of Rust. Well, one of the selling points of Rust is safety, and this really forces you to use it in a very specific way. So I do appreciate that, but I mean, look, I'm a youngster in Rust, if you can put it like that. So maybe that's why I found it difficult, but I found it much more involved than C++. And of course, and I had to learn the whole iterator setup. What you can do with iterators, what it actually means, and in C++, you would have just done, as I said, pointer arithmetic, on dynamic arrays or something, or static arrays, doesn't matter. But I think it would be pretty much more straightforward. So this was challenging for me, to be honest. Yeah.
Do you want to go over the details of one of the functions to see so we can
Well,
uh,
I'm just trying to get to.
go for a simple function and then maybe later on a more complex one.
Okay.
So we can have a feeling of
Yeah.
how this code looks like.
Okay, so we're out there. So I
So
just want
even to
to.
transpose, I don't
Oh,
know if it's difficult.
okay. Yeah, transpose is shit. There we go. Okay. Okay, so this is. So remember, vector matrix is a flat vector. So basically, what I do is when I come into this function, I just declare a mutable vector, a generic vector of type T, which is what the original type is. And it's declared with the capacity of the one that I'm entering in. So just to go back to something I said previously, is that I was learning as well. So there may be some way of doing this in place, but this I just declared a new vector, kind of vector, a result vector, which you can see I later wrap it into the matrix that I return, if you like. So and then so for each row index in the number of columns. So we have number of columns. So this is for each item in the row. Oh, I have to really scratch my brain here. Oh, that's right. I used the skip iter to actually skip the actual offset. So that I don't want to actually use this example because this doesn't really show using skip and the iterator function skip and step by, which I actually use quite a lot. So anyway, but we can continue with this. Then we have we just use a skip iterator to get to the correct one, because remember, if you have, where is the example here, there we go. So we want to transpose that, so that is the row, and we want to make the row the first column, right? So you've got to go through the first row and write the first column, but the problem being that you're writing it into a row dominant vector, which is what this result vector is. So you've got to go and say, if I transpose this, you've got 1, 2, 7 going down and 3, 4, 8 going down. Okay, so you have 1 and 3 being the first row now. So 1 and 3 will be the first two elements of the new vector here that I'm writing.
I'm
So
but
so you can see in the result vector, sorry, I'll be with you now, Gabo. We actually just build it up row by row.
right.
Yes, Gabo, ask a question.
No, I was just wondering if the transpose is not just taking the XY element in the matrix and put it in the YX spot.
Right. Yes, you can. So if you if you have a way of accessing the elements XY, which I do have up here, but
I mean,
I'm trying
it's
to,
an array, right? The whole thing is
yeah,
just one long array.
well, it's resembling an array, but it is stored as a flat vector.
So it's
That's the,
vector, sorry, correct.
yeah, flat vector. So the thing is that I can write this by just saying for each row, for each column, swap, go get element xy and make it element yx, and I have the accessors. I think I've got it. Sorry, let me just find it up here. Where is, oh, there, index. So I've got index and index mutable, which will give me access to the actual xy coordinate, if you like, or the row column coordinate, and then just using index mut to set it to yx, if you like. But that means that you are calling this routines many times, okay, in a loop. So I would rather, for the sake of efficiency and speed, when I look for, which I've lost now. I would rather do it directly on the vector and pull chunks out of it than actually, so I'm saving a little bit. Okay, not much, I guess, but this to me is more efficient than just sitting in 2 for loops and swapping rows and columns around, row and column items around. I could be wrong, but that was just my thought on this. Sort of happy, Gabor?
I'm trying to understand. Yeah, the skip
Okay.
iter. What is that?
This is, I defined it up here. So that is just a way of defining an iterator that skips a certain step size through. So you could, instead of using this, and as I said, this I used in the beginning, and later on I used the iterator, actual iter functions, step by and skip, which would do the same thing as this.
Okay.
So what I'm actually saying subtly is that this would probably needs to be rewritten at some point. but for now it works. Okay, and it'll become clear why I just sort of went on without really being too fussed about this. Okay, so I don't. Okay, hang on. Let's get some order here. Go. Where was that again? Can't remember. There we go. Okay, so that's a very easy function, which, as you rightly say, probably needs to be rewritten. I'm just trying to think if there's not something else that is probably better. Submatrix, you see. Yeah. Okay, so again, the idea is you want to grab a chunk out of this. Okay, that's not. You want to grab
some rectangle
from here. Yeah, you want to grab a little block out of it, and the way you specify it, you say inclusive. I want to from column 3 to column 7, and from sorry, row column. We always work row column. So row 3 to including row 7, column 2. So you can. It's a little slice out of there. So basically, we just check that it's the correct rows. Right. Iterate, get an index going, enumerate. Then we will skip. So we want to position ourselves. So if you imagine just visually, if you want to extract a chunk out of here, and remember that it's stored row dominant, you want to first get to this row, and you can just strip out the number of row elements, if you like, because they would be adjacent to each other in the storage vector. So this would be straightforward, if you like. So you would remember this all up here before you get to this element here. This all will be in a flat vector. So it's a row, then the next row, next row. So you've got to skip the number of columns times up to this row. And then you have to skip what the index is that you want to extract. So you want to skip 3 rows times how many columns is in a row. So that, and then you want to add on another little piece until you get here. So that positions you here. So I think you can see that exactly what I've done here. The problem, not the problem, but something that probably could be changed is that I'm using one indexing for use, but obviously it starts at 0. It's 0 indexed. So that's why I always have these -1 nonsense, and it gets a bit tedious. But anyway, be it as may, the number of columns times the number of rows above the element, and then plus where the column is that we want to extract. You can see col's start is the first one here in the range. Okay, so is that sort of reasonably clear?
Yeah, I think so.
What I'm doing? Right. So then
you're using assert to verify the
yes. Well, this is just to make sure that I'm not specifying in my rows and columns something that will sit outside. That there isn't enough rows for it to sit in here, if you like. In other words, I'm not wanting to extract this submatrix that is larger in some dimension than the matrix I'm given.
Right.
Right. So that's all the sort of stuff the search that I do there. So then the step by, geez, I'm trying to think what I did here. I know I extract little vectors and then I flatten them, obviously. This is what's happening here. Oh, sorry about that. Step by. So I get to the right position, then I start iterating. just thinking, why am I not iterating by one, stepping by one, first of all? Oh, well, guys, sorry, I should have spent more time prepping it. I can give better answers.
It's fun reading code, even if it's yours.
Yeah, it's as I said, I haven't spent time on it, and I've been so deep in trying to find a memory leak on a big Golang server, and it's yeah, my mind has just not been on this at all. Okay, anyway, um, if there's real interest, we can come back to this at some point later when I will make time. From the beginning of April, I have more time again. So maybe we can make another arrangement. I can look at this. So maybe see this as a sort of a high level view to start off with.
Okay.
Anyway, so the moving on from this, which I hadn't really considered in the beginning, but it became obvious that if I wanted to something that would be actually useful in terms of machine learning, I would have to move into tensors. So tensors is just a higher dimensional form of a matrix, or a higher dimensional form. A matrix is a higher dimensional form of a vector, and a tensor is then a step up from that. So generic n dimensions or rank. So this is where I actually did my last work, and it's also probably the most, from a Rust perspective, the most mature. So again, I declare a tensor object, generic tensor object, using a flat data structure. I have the shape of the matrix. Okay, now I just want to actually halt there and interrupt myself again and say that what I actually was trying to do, and I actually had to go back and change the names a bit here because I had the right idea, but I had different names for this. I think I had dims here instead of shape. But then I've done quite a bit of work in with TensorFlow in Python, etc., and in the array, and NumPy, sorry. So I had in the back of my mind, it suddenly came to me, I want to write something in Rust that somebody with a Python machine learning background would feel comfortable in, well, reasonably comfortable in using. I don't know if that's a pipe dream, but that's sort of where I was going with this. So that's why I changed this to shape. And strides I had from the beginning. So let's go. So again, I'm sitting with row dominance, but whereas previously in a matrix, you have a row followed by a row, followed by a row, you now have a more complex setup where you can have n dimensions, non-specific. In other words, you can access the way that you access an element becomes very much more obtuse, if I can put it like that. And so that's why in the beginning, when I establish the struct, I calculate strides. Now, strides is a way that you can use to calculate offset in the vector to get to an element of a certain coordinate. Given a coordinate, you can use strides to get to that element. I will demonstrate it shortly, how this works. So that was pretty straightforward. And in the next line comes to exactly what I've been talking about. So if you have an object declared like this, with when you declare a new one, it automatically calculates the strides because it has got the dimensions, the shape, if you like. So basically, a stride is the index of a coordinate, and you can see the coordinate you specify as a vector because it can be of any dimension up to, say, 15, 20, 30, whatever, pick a number. So obviously a good way is to present it as a vector. You could probably find other ways of doing this. So here I specify a coordinate as a vector, and we can look at an example. I see I don't have an example up here, but yeah, we can look at an example. So, but more importantly, you can see that I take the data, which is a vector, and I step through the coordinates that I were given, this vector. I step through it, and at the same time, I'm stepping through the strides, because the number of strides, this vector equals the number of coordinates, and I just do accumulated multiplication. So strides are set up that I can actually get exactly to the offset in the vector for this coordinate. It takes a bit of thinking maybe to visual. Well, you can't really visualize because you're starting to work in, you don't have two dimensions as in a matrix. But this is, if you think about it long enough, it'll become obvious. Well, not obvious, but what I'm doing. So there's just the mutable setting that you can assign values back. Right. So here is the sort of generic implementation of tensors where you have stuff like, oh no, sorry, my apologies. That's not. Yeah, no, it is. What am I saying? No, here, standard functions. So anyway, this is just what I wrote because I got tired of, I wanted to display tensors properly. In other words, like Python would. So this is the sort of display that I wrote, formatting it properly. We'll get to that in a moment as well. I'll actually write, we can do a real-time example of using this. I'm much more comfortable talking about tensors because it's the last thing I did, so it's probably more recent in my mind. Recent being a month and a bit ago. Okay, so these are the general functions. New, declaring it, so you specify a shape, you specify basically all the dimensions in a vector, and then you give it the data vector. So the data vector is flat, but the shape gives it its tensor characteristics, if you like. So you can see when you declare new, I can easily calculate the strides because I have the dimensions, and the strides are simply just an accumulated multiplication of, for each one you calculate one less, I think. And you put it into the strides. So this is what I'm doing here. Yeah, so I'm starting at 1, where index is 1. So the 0th stride is skipping 0. No, sorry, 1. Yeah, start at 1. Skip 1. And then accumulate. Yeah, everyone's sort of familiar with this syntax. The fold, the initial value, and the closure. What I do find very I don't want to use the word annoying, but in a way it is this sort of dereferencing and cloning. And again, I know that's the Rust safety guarantees that things will disappear when they need to disappear or go out of scope. But still, writing the code for it can sometimes get very very challenging, I find. Anyway,
Okay.
sorry, that's my dog.
No problem.
getting excited there. Anyway, so this is just setting up the new tensor, and then so you have shape, strides, and the actual data vector. Yeah. You can also, okay, so just now to sort of add on to the discussion about writing something that would start to be slightly vaguely familiar to Python users. So there's a tensor library in Python called Tensorly. I don't know if anybody has looked at it. I mean, Gabor, you do some Python as well.
Yeah.
So Tensorly is quite an advanced library in terms of using tensors for numeric computing. So it's not like TensorFlow where you specifically maybe writing a neural network and you're training it, etc. That kind of thing. It's more you can do what they call tensor contraction, which we'll get to in a moment, and you can do factorize tensor into more as the sum of more usable tensors or even usable matrices. You can sort of change it and make it. They're all sort of numerical tricks to make it easier to work with tensors and to manipulate them and to understand what you're actually trying to do. So having said that, I've never really worked with it directly myself. Okay, so we get to subtensor. Right. So one of the big things that I discovered right in the beginning is that because you are in matrices, it's very easy. You are working with 2 dimensions and there's only 2 dimensions, and that's always 2 dimensions. No problem. If you are writing a generic tensor that can be anything, then it almost forces you to start using nested functions within to do things. So this also was like a very tricky concept to get used to, because you could almost think as a tensor where you are, if you want to get to an element, you have to, how can I put it visually? You must drill down the dimensions until you get to the actual element. So that's sort of very strange, may sound very strange, but if you write the code, one starts to understand that's sort of what is happening. So, for example, here, if you want to get a subtensor of a tensor, you first have to work on all the dimension levels, and at each one you've got to drill down to the required dimension and extract an element. That sounds very strange now that I say it out loud, but that's really the thought process that's gone on here.
Yeah. After 3 dimensions, it's getting a bit hairy.
Yeah, well, 3 dimensions you could probably still visualize, yes, with X, Y, Z,
Yeah.
or Z. I don't know what you guys call Z in South Africa. We call it Z. Zeros are standard stuff, this is if you just want to. So this is all. What happened is then I started looking at Tensorly and I say, what does it have? And I want to do the same stuff. So zeros is just to create a tensor of these dimensions, or shape, if you like. So that's probably shape would be a better thing to put in there. And they're all just filled with zeros. These are all filled with ones. These are filled with a certain value t, and this is filled with a certain value range that starts at t and go up. Yeah.
Yeah, I think dimensions would say that like it has 3 dimensions or 4 or whatever, and the
Yeah,
size
yeah. But it's just
describe actually.
It's just that in Python and Tensorly and even NumPy, they use shape. So I sort of, there's if I wanted to make a product that I sort of can really commercially market or sell or punt, not even commercially, but in seriousness, I would have to go through this and make it all and standardize it and make it much more, how can I say, rigorous. That's the one thing. The other thing is I'm sure that a lot of optimization can be done, which I'm, if in a Rust perspective, not I haven't gone down that road at all, and which probably needs to be gone down. So I'm not making any. I mean, I've done no benchmarking against anything else. So there's a lot of work that needs to be done for this to be a robust, rigorous library for sure.
And
And I
we are
think
getting close to the 1 hour. So
I am. Oh, I'm rambling on endlessly. My apologies. Anyway, so
yeah, I have to
let's
wrap up soon, I guess.
yeah, so random and stuff like that. And I think the biggest and the most difficult thing that I've done up to date was contracting a tensor, and that so you, using Einstein summation notation. I don't know if anybody's familiar with that. So you have basically two tensors, and you basically want to contract a tensor ijkl with mkni, which means you're taking the third dimension and contracting it with the second dimension, and you're taking the first dimension and of the left hand tensor and you're contracting with the right hand. And what you get, basically contraction, you are shrinking the dimensions, you are melding, if I can use that word, adding these two tensors together, and you will end up with a tensor of dimensions j, l, m, n. Right. So, and contraction was extremely difficult until the penny dropped. So here's, okay, so Einstein notation is just a way of writing it out understandably that uh, tensor algebraists use. But the actual underlying routine is the contraction routine. And that, once you realize that a tensor, you have to drill down through all the dimensions, and at the end, you end up with a matrix at the bottom of drilling down. And once you have that sort of idea in your head, then it's just a question of rearranging, um, finding the correct, going through the dimensional drill down to find the correct element in the matrix underneath. That doesn't sound very nice, but anyway, that's what it happens. Anyway, so that's basically is sort of where I'm at. As I said, contraction was the biggest thing. Oh, almost the first thing I did with tensors is I wanted to do a creation macro, and I had to resort to this was very interesting. I had to resort to writing a separate crate that contains a, what's this tensor called? What's this macro called again? Uh, Somebody help me here. It's not, your normal macros, or you can write it in your crate, but this is a specific execution macro, process macro. Sorry, yeah. And that's the first time that I had to use a nested function. I think here. Is it here? Flatten array. Yes, I used flatten array. It's the first time I had to use it. So what I was trying to achieve here, and this is, so if we go back to the tensor library, which uses that macro in that crate, is that you can establish tensors by doing this. And that is fantastic. I love that because and you can, I mean, this is a like a 12-dimensional tensor, which you can establish like. So this is just a stupid example, but you can see, and that establishes the shape of that and the strides of that, and that's the actual data is still a flat vector. Anyway, that's about it. So I would love to, if you guys at any point want to chat more about how I did it, I'm happy to have future interaction on a one-to-one or one-to in a group session, but only from April onwards, because at the moment things are hectic on my side. That's it. That's a wrap from me.
Well,
I hope.
thank you very much. April is not that far. It's like 2 weeks, right? So.
Yes, no, exactly. But that's why it's a bit tense at the moment, because there's lots of pressure and there's a substantial bonus involved if I sort things out, so you can understand.
Good. Good. So thank you very much for your presentation. By the way, your information, I put the link to the Git repository in the chat, and it will be under the video as well. You will find that, and a link to your LinkedIn page, so people will be able to contact you if anyone is interested. So thank you very much for your presentation, and for everyone who listened, and for everyone who watched the video. And just remember to like the video and follow the channel. Thank you very much. Bye-bye.
Thanks, Gabor. Thanks, guys.
Bye-bye.
Cheers. Bye-bye.